In this last lesson in the unit, we're going to look at some applications of distance, speed, and time, and how we can use calculus to solve some of the rate of change problems that occur between those three things. Just a quick reminder, the distance always equals rate times time, or rate equals distance over time, or time equals distance over rate. It's kind of a really important idea we have. Okay, we're not going to learn any new calculus ideas. That is, we're not going to learn how to take derivatives. We're just going to learn how to apply them a little bit. So let's look at this first example here. We have a pair of scuba divers wishing to dive on a wreck 0.4 kilometers offshore from a point 0.8 kilometers from their present position. So we kind of have ourselves a little bit of a diagram right here. We have, say this is the shore, and here's the wreck. Well, they're down here. They're 0.8 kilometers downshore from the wreck. Okay, and we know the wreck itself is offshore, so that distance there, 0.4 kilometers. And this makes a right angle here. Our divers can walk all the way down the beach, 5 kilometers an hour, or they could swim directly from where they are on the beach. Actually, let's move our dot here, just we're actually on the beach here. At 3 kilometers an hour, and they want to figure what's the least amount of time it's going to take them to get to the wreck. So we have some options. We could swim all the way there, and that's an option. We could walk all the way down the beach and then swim out. That's an option. Or we could walk partway down the beach and then swim out. Okay, so we kind of want to figure out which of these is the best option. And if so, how far to walk and how far to swim. So we can solve all three of those problems simultaneously. If we think about, I'm going to pick a point, a random point. I don't know where that point really lies. It might be I should walk this far and then swim, or theoretically this point could move over to here and I should have walked all the way down and then swam, or theoretically this point could move back to here. I should just swim right off the bat. We're actually going to solve that point, all three situations at one time. But we're going to start off by drawing it somewhere in between the two spots. Okay? We don't know where it actually lies. Okay? So what I'm going to think is, I'm going to walk this piece, and then I'm going to swim this piece. And those two things combined are going to minimize my time. My time is made up of some walking, maybe. It may turn out to be 0 walking is the best, plus some swimming. And again, I could end up with no swimming. I should maybe just walk the entire, well, actually, I guess you have to swim part of it anyways, right? This part right here has to be swum. But I'm gonna have to figure out how do I use these two things in combination together. So if you remember back to when we were talking about we had our two objects moving against each other, and we always figured out that our time can always be found by distance over speed. And we kind of want to minimize our time here. So I want to talk about each of these sides of my triangle, if you will, in terms of time. Okay. I don't know how far I should walk. I'm going to make this x, okay, which would make this piece in between here 0.8 minus x. Somebody might be saying, well, why don't I make this x? And then this would be 0.8 minus x. And that's fine too. You could do that. I just think it's easier to have less variables on the sides of my triangle. Because you don't only deal with triangles, in particular right angle triangles, you can use the idea of Pythagoras, right? So I want to set up an equation dealing with time, which is my distance over my speed, for each of these pieces. So the time that I spend walking, well, how far do I have to walk? The distance I have to walk is this bit. So the distance I have to walk is 0.8 minus x. What speed am I doing that at? It tells me in the question that I can carry my gear at 5 kilometers an hour. So an expression for my walking time is 0.8 minus x over 5. My swimming time is this piece right here, right? This hypotenuse of the triangle. How can I find that? Well, that's the square root of whatever x squared plus 0.4 squared is. So if I want to go at my swimming time, my distance is x squared plus 0.4 squared, and that's my distance. So distance over speed, they told us in the question we can swim at 3 kilometers an hour. And now I've got myself a equation for time in terms of x. I want to minimize this time, which means I want to take a derivative down the road. So I'm going to simplify this a little bit before I try and take derivatives, okay? So I'm going to divide the first fraction, both these things, by 5. So I'll end up with 0.16 minus 0.2x. Over here on the next piece, I'm going to write this as a fraction. So 1/3, that's the same thing as divided by 3, times x squared plus 0.4 squared is just 0.16. And the root sign, we know that's an exponent of a half. So I've got a slightly different version that's going to allow me to take my derivative easier. If I want to minimize my time, I want to take the derivative and set it equal to 0. So let's take that derivative. The 0.16 will be gone. I'll be left with negative 0.2. I'll have 1/2 times 1/3, which is 1/6, times x squared plus 0.16. Gotta subtract the 1, so minus a half now, times the derivative of the inside is 2x. As we've always done, when we want to solve this, we want to set up for cross multiplying. So I'll bring the 0.2 over here. Let's think about this in terms of a fraction. The 6 on the bottom, because I have exponent of negative 1/2, I can bring that to the bottom. So I'll get, actually let's write it with the root sign there, sorry. So what's the root sign? Root x squared plus 0.16. And the 2x is left on top. Okay, it's ready for cross multiplying, so let's cross multiply. 1 times 2x is 2x. 0.2 times 6 is 1.2 root x squared plus 0.016. We're just cross multiplying there, right? To make that easier, I'm going to have to divide both sides by this 1.2 piece, okay? So I'll be left with just the root on the right-hand side. So I'm left with the root of x squared plus 0.16. On the left-hand side, 2x divided by 1.2 gives us 1.66 repeating x. I'm trying to solve for x, right? Trying to solve for x here. So I need to get rid of this root sign. To get rid of a root sign, I can square it. If I square one side, I have to square the other side. 1.66 squared comes out to about 2.77 repeating, an x squared on it, and my root sign is gone from the right side. I can solve this. 2.77 repeating, x squared minus x squared. Oops, that should be x squared there, sorry. Equals 0.16, or in other words, 1.77 repeating x squared equals 1.16. Divide both sides by that 1.77 piece, and we'll end up with x squared equals 0.09. And if I square root that, x equals 0.3. So, what did x represent back in our diagram? X represented how far it was from straight across from the wreck to the point they should walk. The question was, what course should they walk? So if this is 0.3 here, and this piece here is 0.8 minus 0.3, which is 0.5. So if I'm going to answer this question, well, where should they walk? I need to say, therefore, they should walk 0.5 kilometers down the beach, then swim the wreck. And this is how we can apply minimizing time to solving these kinds of problems. And now, the math involved here is not hard, but there definitely is a lot of steps. And you gotta be careful sort of on each step. Unfortunately, this time when we do the cross multiplying, this point right here, it doesn't eliminate anything, it doesn't get rid of the whole bottom. You actually end up with the whole bottom. Okay. Remember, our objective was to figure out an equation for time, so you got to figure out your walking distance and your swimming distance. And I think the idea of Pythagoras is really what you want to use. And I would always suggest making the top of the triangle x, or the side of the triangle x, and what depends on what the case may be. So it just makes it a little bit easier to work with when you're doing your derivative later on. Okay, you guys are going to try one. Same idea, same kind of process. See if you can do this one yourselves. An island is 100 meters from shore, and the fishing camp is 500 meters down a straight shore from the closest point to shore. So here's my island, straight to shore, down the shore. Okay, this is 100 meters. We know it's 500 meters down the shore to the fishing camp. So here's where the camp is. Joe can row from the island at 40 meters per minute and walk at 60 meters per minute. Where should he land his boat? So he's going to go from the island somewhere on the shore and then walk the rest of the way. So I don't know how far away he should go. I do know that when he does land, it's going to be 500 meters minus however far he rowed. I know my distance along the diagonal is going to be the square root of x squared plus 100 squared. If I use those two things combined, I can create myself an equation for minimizing my time. So as we just said a second ago, time is always distance over speed. So he's got his rowing distance and his walking distance. So walk plus row. How far does he walk? He walks 500 minus x meters at a speed of total 60 meters a minute. His rowing, x squared, might as well put the 100 into 100 squared, and he rows at 40 meters a minute. So here's the next expression for time in terms of x. If we want to minimize our time, so we're going to take a derivative. We should simplify this first. So 500 over 60, well, it's kind of hard to simplify. Let's just leave it as 25 over 3, just reduce the fraction. Same thing over here. Can't really divide it by 60 without making big long decimals, and I want to avoid those. The next piece, let's put our fraction out front, times our exponent, which is x squared, plus 100 squared, which is 10,000, sure, to the exponent of 1/2. Now we're ready for derivative. And I want to minimize this, so I want to make it equal to 0. 25 over 3 will be gone. X over 60, well, that's just 1 over 60 now. Plus my 1/2 times my 1 over 40 is 1 over 80. My exponent is going to have to subtract 1 from that. So negative 1/2, and inside I get 2x. I want to set this equal to 0 and then rearrange it. So the 1 over 60 comes to this side. And on this other side, I'll have 2x. And I have 80 root x squared plus 100 squared. I just didn't bother squaring the 100. I can do that at any point if I want to. Okay, cross multiplying. I end up with 80 root x squared plus 100 squared equals 120x. I want to divide both sides by 80 to make my life easier. So I'll have x squared plus 100 squared. 120x divided by 80, that gives us 1.5x. That's much nicer to deal with. Okay, to get rid of our root sign, we got to square both sides. So if I square the left side, the root sign's gone, and 1.5 squared, that gives me 2.25x squared. Okay, I'm finally going to do the 100 squared, so it's 10,000. 2.25x squared minus x squared Gives me 10,000 equals 1.25x squared. Divide both sides by 1.25, and I'll get 8,000 equals x squared. And if I square root 8,000, I end up with approximately 89.4. What did x represent? X represented how far down the beach, what's his name, Joe, can land the boat. Okay, he should go this far down the beach before he lands the boat. So, how do I answer my question? Therefore, Joe should aim for a point 89.4 meters down the beach towards the camp. Okay, it's not 89.4 meters from the camp, it's towards the camp. Okay, there's our second example. Okay, last one. Again, you guys should try this one first. See if you can figure it out yourselves. If not, check back in with me. Electric power for a community on one bank of a straight river. Give yourself a river here. Get a river. Here's my river. Straight. 200 meters wide. So I know this distance right here is 200 meters. Must come from a power station on the opposite bank of the river. So that's what our power station right here, and our town will be over here. Town power. Okay. What does it say? It comes from a power station opposite the bank of the river, 500 meters downstream. So downstream, so this distance here has got to be 500. I think these are all meters here, right? Yeah. It costs twice as much to lay cable underwater. A path should be chosen to minimize costs. So I need to make myself an equation for costs this time. So no matter what, I'm going to have to cross the river, right? I have to go across the river. At some point, I have to make my way down to the community. The question is, do I go straight across and then down, or do I find some point in the middle where I can go across first? So obviously, we have the 200 here. We have the x here. And we have the 500 minus x right there. Okay, same kind of question, except we have costs involved this time instead of time. So let's set up an equation for costs. The costs depend on the land piece plus the underwater piece. What did it tell us? It told us on land, it costs twice as much to lay a cable underwater. So if I think of it as a dollar for every land piece, well, my land costs are just 500 minus x, if you want to, times $1 for each of that. The underwater piece is $2 for the distance underwater. Well, the distance underwater is the hypotenuse again. So in other words, the square root of x squared plus 200 squared. It's about costs this time. There's an expression for costs in terms of x. I want to minimize my costs, so I'm taking my derivative equal to 0. Now, the number 1, I put out front, right, this thing right here. It doesn't actually have any effect. So when you're taking a derivative, you can ignore it. So the derivative of 500 is gone. The derivative of negative x is just negative 1. It's just that piece. This next piece here, what do I have? Really, this is like saying x squared plus 200 squared to the 1/2, right? So 2 times 1/2, that gives us 1. Inside the bracket stays the same. Exponent, got to subtract 1. Derivative of the inside, 2x. If I rewrite this, I end up with 1 equals 2x over the root of x squared plus 200 squared. Good old cross multiplying. This is kind of nice because I have the number 1 and I have the number 1 underneath it, so it makes my life easier. We can square both sides. We've got 4x squared. We can rearrange this. Put the 200 squared becomes 40,000. So I'll get 3x squared on the right. Just bring this over and subtract it, right? 400,000 divided by 3, well, or sorry, 40,000 divided by 3, not a nice number, so I'm just going to leave it like that for the second. And to get x, I'm going to square root whatever 40,000 divided by 3 is, which if you use your calculator property, it should come out to approximately 115.5. So the question was, what path should be chosen to minimize costs? Well, x is 115.5, so how much should be on land? The land piece should be all of this. So 500 minus 115.5 gives us 384.5. Okay, so therefore, the first 384.5 meters should be on land, the rest underwater. And the whole idea of that is so we can minimize cost. Okay. If you want to figure out how much is actually underwater, you can. You can go back up here and figure out the hypotenuse piece, how much of that's actually underwater if we wanted to. It didn't ask us that. It just said what paths should be chosen. Okay, so there's some last little applications of how we can use calculus to minimize time and costs.